Hello everyone, today we'll continue our experiments of design 2 lab experiments. We already, if you watch YouTube, you will find 4 experiments. 3 of them was for the DC motor experiment and 1 was for the HVAC system. So today we'll continue our PI controller. We will apply a controller of PI, proportional integral gain, in order to control the temperature of this system. Simply, you can go back to videos in order to see the setup, but simply we have our room in here. We have a heater as a source of heat. We have a sensor for temperature, and we have our controller. We can send data between hardware and software. So what will be our experiment for today? If we open our local disk D and HVAC trainer and VI, the software PI control, double click PI control, we will have our software, LabVIEW software open. Yes, LabVIEW software open, and at the same time we will open our PDF manual. It's for student manual. So if you go back to the software, we want to see the elements. It's exactly similar to previous experiments if you watch them on YouTube. We have our signal for voltage, our temperature scope. It has set point and measure point. We have digital scopes, and we control the signal through this element, signal generator, and also the control parameters for KB and KI, because we have PI controller. We can stop the system from here, we can run from this button, and we can control the heater on and off from this button. This is to select our device. So this computer is attached to device number 2. Device number 2, and run the experiment. We will see that our temperature starts rising, and we have a scope of 23. But now the actual temperature is only 19, because this is the room of temperature of this room, the lab itself. But if I select the heater on, you see that heater is on now, and the temperature is increasing until it reaches that value. So what is this jump? What is this current jump? Because we set our signal into a square wave. This is a square type of the signal. It's a square wave. Sometimes high temperature required, and sometimes low temperature required, and we are just following that signal. So if we reach this element, that means the controller is able to find a good fitting between the set point and the measure point, but unfortunately we couldn't. So the square wave is changed now, and now we are following the low temperature, which is easy to follow because we already have higher temperature. So the new cycle will start. This is the new cycle, but our actual temperature, it has some delay. It cannot follow at the same time immediately with the rise. So with a delay, it will catch this signal at maybe, we just wait, by now from 70 to 90, maybe 15 seconds. So now we are good with the same signal, with the same temperature, until we have the new cycle. Of course, we can control the time axis starting from 0. We can also control the y axis. So we will increase this to 27 and keep it starting from 22 to have a better view of our cycle. So what is the difference between these two cycles? This one is transient. So the system is heating up. This is the first reading we cannot consider, but starting from this second cycle, all cycles will behave the same because it's repeated. So maybe in the halfway we will catch, and then we will reach the same value. So this behavior will be repeated through all cycles. So what will be the objective of this experiment? We want to study the effect of changing the parameters KB, proportional gain, and KI, integral gain, and their effect of the response on the temperature. So you see that if I just change the KB into 8, for example, random value. Let's see the next cycle how it will behave because of high KB value. So this value, it seems like the rise time is faster, but we cannot let's just wait. Let me prepare that. Instead of 200, let's look until 300, for example. Okay. So having KB higher, instead of catching the signal in halfway, we still, okay, that means increasing KB will increase the delay, and we are not able to catch the signal, and the square wave is done, and new wave will start now without reaching our value. So this is a sample of how the effect of KB and KI on the system. So to have our experiment run, let's stop this and go back to our manual, the same manual of last experiment. This is HVAC, heating, ventilation and air conditioning system. This is the experiment we did last time. Last time we did the section 1, on-off control 4.1. Today we will go to section 2. Where is that? 4.2. Yes, section 4.2. It's a PI control. So the same procedure, run the system, make sure the fan is working, adjust the scope of temperature, calibrate the sensor. We did it last time. We just click calibrate in order to make sure the readings of the sensor are accurate, and activate the heater. We did that, heater on, and adjust the scope of the temperature. That's ready. So to start, make sure that amplitude is 0.5, frequency 0.02, and offset 1.5. 0.5, 0.02, and 1.5. Good. What else? Make KB 4, 0.5, 1, and 1. 4, this is 4, 0.5, 1, and 1. And now we are ready for the cycle. We want to see the effect of of KB. So we will fix KI to 0 and then change the effect of KB between 2 and 10. So we will go and put KI 0 and study KB from 2, and now we are ready to start the system. Start and calibrate. So each 50 seconds I'm going to change the value of KB. Where is the actual value? We need to set our reference. So if we start from 20, for example, now we can see our actual temperature. If you watch the YouTube video for the last experiment, we mentioned that the temperature systems, they have low response time. It's not like the DC motor. If you just click, then you will see the effect immediately. So the effect of KB2, we will consider 50 seconds at least, or more than that, to make sure that the system of the temperature is changed based on that value. This is 50. Now we can go and see 4, for example. So starting from 50 to 100, the effect of the KB will be 4. And you see that we can see the difference. The gap between the set point and the actual value is high, and now with this amount of 4, the gap is reduced. The good thing is that we can compare with cycles. So this full cycle going up, straight and down, we will wait for the second cycle to be completed and then compare the result. So now you see this is far from the cycle, this is close, this horizontal line, the actual line, the actual temperature is very far, and now it's much better. So what if now this is the end of the cycle? Let's make it 6, and we will compare from the coming cycle. and you see the difference. It's much better than compared to the first 2 cycles. Let's let's finish this cycle, and then we will do the KB number 8, KB 8. So if I make it, or just let's do it 10 for example. So with KB10, you will see that the actual value is much closer to the set point. And now in this figure you can see KB2, 4, 6 and 10, and which shows the effect of KB. So increasing the value of KB will enhance the response to be close to our set point. But remember that KI in this case is only 0. So what about the second exercise? The second exercise, now we will set KB on some value 0.5, and now we will change the KI between 0.25 and 2 in order to study the effect of KI. So let's go back and say that this KB will be 0.5 and KI will start from 0.25, and our test is started at 22 to 5. So 225, the start of our test, and we will make it up to 500 for example. And this is the new setup of KB and KI. You see, KB 0.5 alone with KI 0 would make this actual value very far from that one, but with KI 0.25 we have almost a good response. So let's do the other cycle. We said that the manual said between 0.25 and 2. Let's try and make it 1, KI 1. So we will compare this old cycle with this cycle to see the effect of KI 1. We have an overshoot, we have rise time, that means rise time is reduced, and this is the end of the cycle. So what if we make KI 2? Now you can see that rise time is reduced, but instead we have higher overshoot. So we can put this scale until 350 and we can stop. So 350, 350, and this is very obvious. The values of KI, it was 0.5 I think. Then we made it 1 in this cycle, then we made it 2 in this cycle, and we can see that the rise time is reduced, but overshoot is increased. So now we have this new setup. From the manual we will put amplitude 0.75, offset 1.5, frequency 0.02. 0.75 for amplitude, 0.02 and 1.5. Meanwhile, KB8, KI for 1 and 100. KB8, KI for BSP1, and this is 100. So this exercise, we want to see the effect of anti-wind up reset parameter have on the control signal and the temperature response. So we want to consider 2 things. For exercise number 3, we will put the value of TR100 For exercise number 4, we'll put TR as 1. So we can make two exercises in the same figure. Section 1 with the 100 TR, section 2 with TR equal to 1. So I will make 100 for example, and I will run the system and calculate. I will divide the screen into two segments. So from 0 to 50 I will consider 100, and then from 50 to 100 I will consider the TR value to be 1, and then we can discuss the effect of entire difference. So now I will change this element into 1. And we wait for the second cycle to see the effect and to be able to compare the response with it. So now it comes. So it seems that rise time is reduced this cycle compared to that cycle. Overshoot is also reduced. So this is a clear effect. Good. So what about exercise 5 and 6? So this exercise is still the effect of set point weight. Set point weight is the DSP value. We will look at 0 value and then 1. The same elements. Let's keep KB8 and KI1. So let's stop that. And KB, this is 0 and this is 1. KI is 1. So this is 1. So if we run the system now, we'll do the same. We will make 50 seconds for BSP 0 and then another 50 seconds for BSP 1 in order to see the effect. So we need to have at least one cycle to be able to compare the effect of BSP. So I'll change the BSP now to 1, and let's wait for the new cycle in order to see the effect of this element. So we can see that the effect of rise time we reach in the corner, but here we have less rise time. So more than half of the cycle is matching compared to no matching in this cycle. So we have a clear effect of that element. So for these two elements, for the BSP and the TR, if you want to study more about them, so we can go to our control guide, practical control guide, and see the content is on the BI control, date 29, BI control, the PI control. Let me go down. Speed control, fastly, process control, PI control, turn on, and off control. This one, PI control for extra. So this is the control parameters: KB, KI, VSP, then current tracking, TR, and the filter time. All of them. I think there is one figure in this figure. So we'll find that in one manual. I think it's available in the manual. The figure to explain the effect of those 4 parameters in figure 5.6. This is the effect, not the block diagram. But anyway, so if we continue our experiment, exercise number 7. Now this is the experiment. We want to find the proper PI and KB and KI. We want to find the values of KB and KI needed to control the system without randomly put the values of KB and KI. So how we can do that? We know that given the value of Z is 0.6 and the value of omega is 0.125, we need to find formulas from the manual in order to calculate KB and KI. So if we go back to the control guide, the same section, process control, PI control, this is the formula to find KB. It's 2Z to omega 0 divided by KB. What's KB? KB is the model we found from last experiment. Experiment number 4, we had the value of K calculated, and KI will be omega 0 squared divided by the same element KB. So we need to watch last video of experiment number 4 in order to find the value of KB. So now you have values of KB and KI. If we come back to this manual, exercise number 7 is done. How to find the value of KB and KI. And exercise number 8, we will plug those values into the screen. Imagine that we have our KB 2.35 and our KI equal to 8.2, for example, and then we run the system only to validate those values and see the effect of our calculation, is it matching or not. So how is the performance of the controller compared to the previous controller, the calculated one? Attach the response, and that's it. So the experiment is done by validating those values. So KB, KI calculated, and then you see that we have, for example, for this random value, we have a big rise time and we have no overshoot, maybe small overshoot. So you need to find your KB, KI, and then say that these values are correct or not. So this is the end of our experiment, and thank you very much.